Hello, welcome everyone to today's webinar. We're going to get started in about 60 seconds. We're going to give an opportunity for the folks that are still coming in to get settled. So just one moment, please. Okay, I think it's time to get this show on the road. Welcome again to everyone. Today's webinar is entitled Practical Human in the Loop Machine Learning. A bit of a mouthful, but by the end of this webinar, I'm sure you're going to have a great understanding of what that means. I'm excited for today's webinar. I get to present a company to you that's addressing one of the pressing needs in the ML community today. More on that in just a moment. Just a little bit of preface about HITL, or Human in the Loop. If you're familiar with machine learning, you may or may not know that a majority of ML projects in production today are what is known as shallow learning. This might be k-means based clustering, which is an unsupervised style of learning, some basic regression, the type of inference you'd get from a scikit-learn or a comparable library. Now, moving beyond shallow learning into more nuanced training is difficult. The one reason it's difficult is that it usually requires a domain expertise. And if not domain expertise, then human insights at a minimum are needed. This is what we know. This is known as human in the loop machine learning. So your speakers for today, myself, Chris Burns. I'm an AI ML specialist, solutions architect at Amazon Web Services. Sounds like a mouthful, but it's not really. I have just under 20 years of overall IT experience, the last 5 heavily focused on machine learning. If my resume were a Venn diagram, it could be summed up by me living at the intersection of data scientist, developer, and cloud architect. Also on the call with me today is Robert Monroe, the CTO of Figure 8 Technologies Incorporated, and he's also the real reason you joined the webinar today. So for our agenda, I'm anticipating 3 general categories of listeners today: the data scientists slash aspiring data scientists, the developers slash architects, and the hippos. If you don't know what a hippo is, that's a term of endearment I've given to the highest paid person's opinion. So that's what a hippo is. Now I'm going to give a super quick overview of ML, or the AWS ML stack, as we like to call it, and that's going to hopefully be understandable to those 3 groups of listeners. Now, I'm not going to be speaking long. I'm just the opening act, and we'll get to our featured machine learning competency partner, Figure 8 Technologies, immediately after my overview, followed, of course, by some time for Q&A. So if you have questions, you should be able to enter those into the GoToWebinar console, and we have moderators standing by here that are going to take those questions and get as many answered as possible. So the learning objectives for today. When it comes to the ML lifecycle, before you decide on a model or even a framework for that matter, you have to understand what problem you want to solve. Once you know the problem, the business problem, then you can begin to evaluate the best strategies for tackling that particular problem. And one of those strategies could be HITL. If you've decided to use HITL, you need an effective means for your humans to interact with your ML lifecycle. Humans are limited by their wetware and unfortunately need all the help they can get. Now, the first step in this process for the interaction is to collect data and create a clean data set. I like to call them clean data sets. It's not a professional term, but by clean, I mean a high quality, accurate data set. You've all heard the phrase garbage in, garbage out. For years, it's been a phrase in the IT world, but nowhere is it more true than with machine learning. Okay, so let's get to it. Amazon, we've been leveraging machine learning for more than 20 years. Sometimes that comes as a surprise. You don't always see it on the surface. But many of our assets are built on a foundation of machine learning. So from the very first recommendation engines during the early days of Amazon.com all the way through today, I'm going to touch base on these in a bit more detail soon. My goal is to give you a history lesson. It's simply for you to understand the roots of our ML heritage in order to position today's products and services, as well as our mission, which is to put machine learning in the hands of every developer and data scientist. Pretty succinct, pretty understandable. Amazon and AWS has been bringing down barriers of entry for years, whether it's with our cloud services or retail opportunities for distributors or disrupting the customer experience with Amazon.com. What we're doing now is we're going to bring our in-house ML investments and capabilities to every developer and data scientist that choose to use them. We can do this because of a combination of fast compute, bigger data solutions, and advanced algorithms that we make available to you. Now, if you're not in a position to use this toolkit yourself, we have, just as on today's call, we have our APN, our AWS Partner Network, and we have partners that can bring these tools to bear for you. Now, this slide's a little salesy for me. You have to forgive me if I go off tangent here, but if you're on this webinar right now, then it should go without saying that you know that ML is a pretty hot topic right now. This tries to quantify that a little bit. We've got some verticals over there on the left, and the darker the green, the more appetite for adoption that we're seeing. A couple of call outs on this slide here. One is that we have high tech and telecommunications at the top. Now, that doesn't mean that there's a more of a demand in that field. It means that there's a lot of inherent expertise in those fields that are early adopters and can take on this machine learning mantle, so to speak, and go to town with it. There's plenty of opportunity here in healthcare, education, retail, and other segments. They simply don't have the in-house resources to capitalize on these technologies. And the other call out is 3,000 startups today. 3,000. That's a multiplier of 30 since 2011. Quite a few. All right, so I warned you we'd revisit this, and it's back already. Now, Amazon.com, our sales, at Amazon.com are heavily influenced by recommendation engines. Personalized recommendations are not just limited, however, to consumer and sales. There's health and wellness, tracking the disease progression. That's a very personal topic. Financial services are being more customized more and more to individual consumers. Advertising, media and branding, these are all individualized services that stem from machine learning algorithms we use today. We have fulfillment automation and inventory management. I don't want to spend too much time on the benefits that Amazon.com has brought with our free 2-day and sometimes free same-day shipping, as well as other expedited means, which leads me to our drone fleet, which are still coming soon. Hopefully we'll see those very, very soon, and they will bring a new wave of disruption to the consumer experience. I'm gonna bypass voice-driven interactions, because we have a slide or two dedicated to them next. But the sum of this slide is to understand that we are inventing entirely new customer experiences. Definitely recreating the interface between the consumer and retail. Okay, so voice-driven interactions based on Amazon NLP technologies. If you don't recognize the device here on the screen, that is the Amazon Echo. We have an entire line of Echo products: the Echo Spot, Echo Look, Echo Show, quite a few different models. Now, this is a family of products we started a couple years ago as NLP. A personal story. I'm moving into a new house, and I've put Amazon Echo Spots in every room because, one, they act like an ad hoc intercom system that's great, but also adds a layer of video. So if I hear kids in another room that sound like they're up to no good, I can just drop into that room and tell them to knock it off. Now, as a seg there, I had talked about the Echo Spots and its video capabilities. I don't want to spend too much time on Alexa and the voice capabilities there. I'm hoping everybody on the call is familiar with those. I want to sort of look to the future, lean out a little bit here. the video features that you're seeing now in the Echo Show and the Echo Spots, those are based on our Amazon Rekognition services. Those are all based on computer vision APIs and machine learning algorithms we've developed in-house. The Rekognition video is available to you today. All of these capabilities are available to you, from object and activity detection all the way to celebrity recognition. Again, this is a little appetizer. I'm not going to spend too much time drilling down into these services. If you want to learn more about these, aws.amazon.com/Rekognition. Make sure you use a K in Rekognition. Now this is a still taken from a video that was fed into Rekognition video. We like to call this out for one specific reason. You see the labels there. Those are authentic labels. Those are labels that were inferred by our API, by the algorithm. The one I want to draw your attention to is the party. Nothing by itself in this still would lead you to believe, I'm sorry, of course a human would recognize it as a party immediately. But as far as object and image classification goes, what we do is we add a layer of intelligence, if I could phrase it that way, on top of the object classification. We see that there's a balloon, there are gifts, there are children opening presents. So the opening presents in the party, that's inferred on top of the object classification. That's a nuance I wanted to call out because it's a big deal, and it's moving us down the path from simple object classification to event detection. All right, so that brings me to our AWS ML stack. Now, briefly, at the beginning of this webinar, I talked about the 3 categories of listeners that I'm assuming are on the call. And so I'm going to address all 3 at this time. This, what we call the stack, begins at the top with our application services. Now, these are the easiest to consume. You're going to get direct hands-on experience across our vision, so that's computer vision, NLP, that's speech and language. These are already trained algorithms. These are for the developers. These are for the architects. These are for proof of concepts where you don't need to train your own models. And I'm not going to go into too many detail, but there's a number of great capabilities in these NLP and computer vision services, all available to you over a very clean API. If we drill down a layer to our platform services, we have Amazon SageMaker. That's an end-to-end machine learning environment that links data scientists, DevOps, and decision makers all into one, I don't like to use that phrase, single pane of glass, but one development environment. We have the new AWS Deep Lens that you're going to be able to get your hands on in just a couple of weeks if you missed out at reInvent. That is, of course, a camera that you're able to push models to from SageMaker for inference at the edge. Amazon Machine Learning is our service we launched a couple years ago. So if you have a use case that fits that regression model, it can do multi-classification, binary classification. So some options there for very, very easy to use machine learning. Then, of course, we have Amazon Spark and our Elastic MapReduce. If you are driving your Hadoop workloads and you want to link those to machine learning, then one of those options would be a great choice for you. And of course, Amazon Mechanical Turk. Now, that might not sound like it's a machine learning related service, but another personal example is I'm trying to create a data set around Pokemon. I'm not going to go into too many details why. You're going to have to just trust me on that. And I have about 15 gig of Pokemon images. Apparently, there's about 800 of these individual Pokemon. And I had the choice to use Mechanical Turk or go through tens of thousands of images myself and say, this is so-and-so, this is so-and-so. So it was a pretty obvious choice there. I had to go with the Mechanical Turk. Finally, at this bottom layer, we have our frameworks and our infrastructure. Now, if one of these services out of the box aren't going to work for you, and maybe these platform services, you're not ready to adopt those yet, we provide you the building blocks that you need to create your own ML lifecycle, from the P3 instances, the GPUs, also the FPGA units that we need to update this slide. We support all frameworks here at Amazon. We're not opinionated as such that we're going to tell you to use one framework over the other. You bring your framework to us. It's going to run on our P3s. It's going to run on the GPUs and the CPUs. It might be a C4 instance. We give you the tools you need to run inference at the edge with IoT on Amazon Greengrass. And of course, our pre-existing mobile platforms allow you to get those inferences onto the cell phones, out in the consumer's hands, tied back into your cloud backend. And I do apologize. I know I'm moving fast. I want to get you to the main course here in just a moment. So a couple of names you may recognize are running machine learning workloads on AWS today. All right, and then finally, my last slide of the day. We recently launched, I say recently in the past past few months what we call the AWS machine learning competency. We have a number of competencies here at Amazon. It could be big data, it could be migration, it could be Windows workloads. We recently launched the ML, the machine learning competency for ISVs. And today you're going to hear from Figure 8. Rob Monroe, the CTO of Figure 8, they worked hard to get this competency. This competency means that we have vetted this company from top to bottom. We've vetted their products, and they've met stringent criteria in order to qualify for this competency. And what that means to you, the customer, is that you can trust them with your machine learning workloads because they've shown us the necessary prerequisites to earn this competency. And so with that, I am at time. Thank you very much for your time listening today. I'll be back to handle some questions at the end. And without further ado, I'm going to introduce Robert Monroe, the CTO of Figure 8.
Thank you, Chris. It's great to be here today. And thank you, everyone, for joining the webinar. So my name is Robert Monroe, and I'm the Chief Technology Officer at Figure 8. My background is in a combination of software development and machine learning researcher. So I worked as a software developer for many years, all around the world, from Australia to Europe, to work in West Africa for the United Nations, and now here in Silicon Valley, where I also received my PhD. So I got a PhD in natural language processing from Stanford, and I've worked at a number of companies, large and small, since then. And today I'm really happy to be talking about something that I feel very passionate about, which is human-in-the-loop machine learning. I think one of the most important problems that we're solving right now in technology is how does artificial intelligence and humans work together to solve problems. And I think this is something that we're really just at the start of. So Figure 8, for those who aren't familiar with us, we produce human-in-the-loop AI software, and it's used by data scientists and engineers worldwide. There's a few different aspects to our platform. So we have substantial software around quality control for human annotation. So doing things like when you're getting human creating and training data, making sure that that job is going to the most qualified people, be that based on their skills, their geography, their language, ensuring you're embedding gold known answers so you can track someone's accuracy over time. And then we also run the largest marketplace for annotation work. So we have more than 100,000 people regularly working on our platform, and that varies from crowdsourced workers in more than 150 different countries, right through to a lot of what we call NDA workers, who are people with known identities who can work on sensitive data under NDA and be trained for some of the more complicated tasks you would typically give to a subject matter expert. Well, I flagged those two areas. It's actually the third area that I'm going to focus on today, which is human-in-the-loop processing. So it's how do we combine human annotation and machine learning to solve a lot of real-world problems in machine learning. So you can think about human-in-the-loop processing at a very high level, as you can see in this diagram here. And I will go deeper into each of these. So if you have a machine learning classifier, at a very basic use case, if you want a high level of accuracy out of that in your process, then that classifier can provide, then hopefully you have a classifier whose confidence correlates well with accuracy, and you can immediately trust the high confident outputs. So you can imagine that if you were doing something, like trying to classify whether an object on a road for a self-driving car is a bicycle or not, and you're going over your historical data for this. If you're confident, that's great. If you're not confident, it's something that you might want a human to review. And so you can put certain items in front of humans for review that can go back into feeding your model, so it's more accurate in the future, and then it can also drive your output. So that's the really basic workflow, but obviously there's a lot of different combinations or permutations of how you might implement this. For example, you might have multiple classifiers. So for some of our clients, they'll have one classifier which is interpretable, so we can work alongside humans and tell why it's making an answer, along with a classifier for more scalable selection for active learning, which might not be necessarily interpretable. And then you also might have different strategies for why you want something to review it. Probably the most common method that we see is taking uncertain items, so low confidence items from the classifier, and giving them to humans for a review. And this is known in academic circles as uncertainty sampling. But there's also a number of other strategies that you might employ here. So you'll always want some example of randomly selected items so that you can evaluate your accuracy clearly. And then you also might be looking for change in data over time. So for example, if again with the self-driving car example, maybe your training data hasn't seen a unicycle before, just regular bicycles. And so hopefully you'll have a machine learning algorithm that can tell you not just that something is uncertain, but something is new or an outlier in some way. So this might be another strategy that you would employ to decide what gets in front of a human for review. What all these have in common is that you are being strategic about how you are continually labeling your data set, which is making the machine learning algorithm faster. And as we'll see in some examples here, this will also go right through to determining the kind of interface that humans can use for the annotation component. So human in the loop is a referable approach to most of our clients because it's really what's needed to make AI work in the real world. So for a lot of the use cases that we see, we're only seeing machine learning models that might be 80 to 90% accurate when applied to real world use cases, except for some fairly basic tasks. And often the level of accuracy that's required is a lot higher. And so this has obviously implications for things like safety in the case of self-driving cars or predictive monitoring. It can also have legal and financial implications. So those of you who are joining us from technical backgrounds, and I think it's a lot of you, you're probably sick of hearing about GDPR and compliance, which is a big topic this week. And one of the big changes in policy there that's come out of the EU and that we expect further adoption for is the ability to combine human and machine learning. So the option for an EU citizen to decide that if a machine learning output isn't interpretable, a human can then make that same decision that was previously made by machine learning. So it's great to see increasing sophistication, not just on the algorithmic side, but also on the policy side, who are helping the privacy and the agency of people who are interacting with machine learning systems. So we work in a really large number of use cases at Figure 8. We have the most widely used software for creating training data. So if you speak to your phone or your in-house device, or if your car parks itself, or if you have fresh food that's been monitored between farm and table, there's a really good chance that you have used machine learning that's been powered by Figure 8. And so the training data that we create and the places where we're using human in the loop processing vary from computer vision, and I'm about to go into some interesting examples there, natural language processing, which is my background, data enrichment. So for example, given the name of a company, discovering its address and phone number, data categorization. So this is something that can go across images or video or language, and then audio and speech recognition. So how can we make sure that no matter what language you speak, when you ask your phone a command, it understands exactly what you're saying. So the example, which I think is one of the most intuitive ones for human in the loop processing, is image annotation for computer vision. So this is a screenshot from a annotation component of our platform, which is drawing bounding boxes around objects. So as you can see in this aerial view here of what I think is Dubai, there are many cars driving on this road. And if you wanted to create training data for object tracking for self-driving cars or for traffic monitoring, then that would mean that you would need humans to draw a box around every single vehicle in every single frame. And you can imagine how quickly this might add up. So if you had just 10 seconds of footage here with, let's say, about 100 vehicles at 30 frames a second, So that's 300 frames times 100 vehicles. I should have done the math in advance. I think that's 30,000 boxes in total. Please feel free to correct me on the questions in chat if I didn't get that back over the envelope. And so the time it takes to draw 30,000 boxes is immense. If humans were to do this, either you could distribute it to a large number of people, as is the case on our platform, then it's going to be very expensive. Or if you're doing this in-house, then this might take you even several days just to do 10 seconds worth of video. So this is a great example of how we can integrate machine learning where we can still get human level quality in the data, but take advantage of what machine learning can automate. So for tasks like this, we're able to automatically generate those bounding boxes, either using a predefined model or allowing someone to quickly click on an object rather than carefully draw every single box. And itself will greatly speed up the process. So we'll see often like 2 to 3x improvement just by allowing people to click on an object rather than to have to manually draw those boxes, but still nonetheless allow humans to correct the box if it's not correct in the first place. And one of the most important considerations to think about here, which applies more broadly to combining human and machine intelligence, is are you introducing a bias into your annotation process? So for example, if we simply pre-populated this image of every machine learning prediction, then it's probably not going to get every single vehicle. It might miss a couple, or it might add a couple of additional boxes which you didn't care about. So as you can see in this image here, for this client, they only cared about cars in motion, and so these cars on the left in the parking lot there are not tagged. This is an obvious error that you could see a general machine learning system make. And so the problem here is that you're potentially biasing humans. So humans are more likely to accept the prediction from a machine learning model, even if it's incorrect. And they're also more likely to miss something if you had pre-populated. And so one of the interface options that we have is that a human will initially see this image with nothing annotated, and then they can just go through and click each object. And it's that point that we use machine learning to then size that box. And we find that in the first method, you do get a bias in humans agreeing with what the machines already know. So essentially perpetuating the bias in training data that's already there. But you don't get that bias if the boxes are generated by humans. However, it's slower. And so this really just comes down to your particular business use case. So if you're a self-driving car company, you want as accurate data as possible. You can't miss 1 in 100 cars. That's a really bad user experience for a self-driving car. However, if you're just trying to make an estimate about traffic densities, so pretty much the same machine learning application, you probably don't mind if you're 1% out. So if you think there's 100 cars versus 99 on the road, you're just trying to get an idea of traffic, then that's going to be fine. And so this is one of the human-computer interaction questions that we think about when we're helping our customers solve their use case. In addition to the problem of identifying the initial boxes, we can also then use object tracking so that we can look at the automatically generating the objects between different frames. So as you can see here at the ground level, between these frames, the different vehicles are tracked automatically. And again, a human can look to see where these boxes have followed the objects. And if they feel like they're not quite correct, then they can quickly go back and forth over that video, identify the errors, and correct any of those boxes, which in turn goes back and feeds the machine learning model to make it more accurate. And so the output of this object tracking and allowing humans to edit and correct is often 10x more efficient than just having humans edit raw data. And so you can see the benefits there. So there's really 3 kinds of benefits you get. One is the reduction in cost. So for the same budget, you could annotate 10 times as much data with the same accuracy. There's the increase in speed. So if you have a fixed set of data that you wanted to annotate, then you're going to get there in 10% of the time. And then I think most interestingly, there's also the benefit in that you can now create data for 10% of the cost. So previously, there might have been use cases where it was prohibitively expensive to create training data. Certainly, we see people spending a lot more money on creating training data than on CPU and GPU cycles. And so with this reduced cost in creating quality training data, you're able to think about use cases, whether that's different kinds of computer vision applications like this, or different language applications, or maybe the extension to a language which isn't as widely spoken, where you're going to be able to find margins and create sustainable ways for people to take advantage of AI. One of the things I love that's going on behind the scenes here is that when we look at one of these boxes, there's been a lot of human and GPU cycles which have gone into place in it. So within our platform, when we're predicting a box around an object, this is based off machine learning models that have been trained on millions of past images. So you've got both the machine learning input, which has been we've gone into the predictive classification, and then also those original millions of human judgments around what's an object and what's not an object. So at the end of the day, even if one of our customers only requires one or two boxes around an object, there have literally been millions of human judgments and billions of CPU and GPU cycles which have gone into making that as accurate and as efficient as possible. So I'm now going to do a little bit of a deep dive into some of the use cases that we work on, so you get an idea of what this can look like in the real world. We work across, like I said, a number of areas, so finance, manufacturing, medical, retail and consumer packaged goods, security, aerial imagery, autonomous vehicles, agriculture, tech, and chatbots. So just give you an overview of some of the companies that we work on in these areas. Most e-commerce companies are teams that we work with, and I'll be giving a deep dive into a couple of these. In financial services, working on, again, a number of use cases for sometimes open and sometimes critical data. In media, if you personalize your music selections on Spotify, then we're happy to be powering that. Across IT companies, we have a number of use cases for data enrichment, computer vision, natural language processing. And one of the really exciting up and coming areas is in robotics and automotive. So the ways in which we're supporting everything from robots wandering around your house to the stocking shelves in warehouses through to your cars, which are parking themselves today and hopefully driving themselves before very long. So I'm going to have a couple of examples in e-commerce, and I really want to tie in the business value to machine learning here. So especially those of you who are joining us who are thinking about implementing machine learning for the first time and are HIPPOs. Thank you, Chris, for introducing me to that term. The highest paid decision maker, is that I'll have to double check to see what that was. But certainly it's something we hear from a lot of CIOs, for example. They know they want machine learning in their company, and it's not really clear exactly how you tie machine learning or artificial intelligence to the company value. So I'm going to go through a couple of examples here. And so first one, looking to improve search results to increase site conversion. And so credit for the slides for these examples goes to our VP of product. So before our VP of product joined us, Alyssa was running about a third of IBM Watson's products. So she has a deep knowledge both of artificial intelligence and how it can be applied in the real world. And so the machine learning problem here, to go right to the kernel, is to prove the percent of hero images which feature the product. So for those of you not familiar with websites, a hero image is the top, often banner image, which is displayed when you land on a site or a given page. And it's considered obviously some of the most important real estate on a web page, which can drive traffic. But the business problem here is to improve site conversion. So the business problem is, okay, so once people visit the website, how can we make sure that they've actually purchased what it was that they're looking for? And so you can go from the business metric of improved site conversion to improve search results. So you're assuming that when someone visits the site, they have something in mind that they want, and they're going to search for that. And then search results, like in most places, are put in groups of 10. So then you want to think about, okay, now I'm going to measure the improvement on click-through for the top 10 search results returned. So that's the specific metric that's going to be used to test search images. And then the way to make sure that they're returned correctly is to make sure that in those search results, you have an improved percentage of hero images which feature a product. And so what that means is you're looking to map images of a given product to the right search results. So here's two examples of what these might look like. So individual product images, so products shown by themselves on a white background, or what's known as lifestyle images, so products shown in the context of a room or other furniture. Depending on the given use case and the profile of your customers, one or the other might be appropriate for your website. And it's a choice that goes right down to the machine learning level as well, because computer vision for products on the left in isolation is reasonably good. But computer vision for products in context, especially for very fine-grained product definitions and distinctions, is still very much kind of a work in progress in the computer vision community. And so this human-in-the-loop task comes to figure 8 as a classification problem. And so which of these kinds of images is it in a given context? So is this image a product image or a lifestyle image or something else? So this Purist 8-inch towel bar in polychrome is clearly a lifestyle image here. So the bar is actually holding that towel. And you can see here that this is how those two kinds of images, in this case Home Depot, are using it for the displaying search results. So someone has looked for towel bar, and the hero images are all lifestyle images, showing how you would actually put a towel bar in context. Hopefully, those of you listening at home don't know where to already know how to put a towel bar in context. So this is clear, non-instructional. This is about the quality of the experience for visiting this website. And then below, showing the individual product images outside of the context to give clarity over what exactly would be purchased. And then zooming back out, improving these hero images will improve the amount of people who will then, after visiting the search result, click on something in the top 10. That improves their overall search experience, and therefore it improves the overall conversion rate. Another example, also related to site conversion, is product matching. And so there's obviously like many strategies, some machine learning based and some not, that you would use to improve site conversion. So I think it's interesting to compare these two. So again, we want to improve site conversion. Our customer wants to improve search results. But in this case, they want to improve the matching on text search strings to product titles. So which specific input strings that you're searching for should match with which particular product titles. It's not necessarily a very obvious one-to-one keyword mapping. And so to do this, they want improved categorization of products by filtering categories. So then very fine-grained categories. And then the machine learning task that we're helping with is improving the percent of products which match categories searched. And so this example is for H&M. So when you search for something on H&M, how can you be sure that it's actually matching the particular type of items which are available in a particularly fine-grained search? And so this is what the human component will look like. So you can see that this might have already been somewhat generated by machine learning. So I think you could accurately make a machine learning algorithm that could reasonably guess whether something was a blazer versus some other kind of jacket. But you still want that human to make sure that you got that accurate data to say yes or no, it is a blazer or not. And then in this case, some more fine-grained patterns. So is there a pattern on the blazer? So none, solved other in this case, checked or stripes or dots. What is the sleeve length? What is the fit, slim, regular, or loose? And so these are the kind of things that you can imagine being categories of clothes and also things that people would want to search for. And so we're able to help enrich the metadata around each of these products in order to improve those search results. So here's another example here. Was the closure of the jacket. So you would click buttons here along sleeve length. I actually don't know what kind of sleeve type this is, but one of the nice things about having a human-in-the-loop platform like this is that there'll be little information boxes which will be able to help the humans make these kind of classifications. And there's obviously no hood there. And so what that means is that you can get some fairly fine-grained distinctions in searches then turn up in your search results. So in this case, someone has searched for a shawl collar jacket. And again, this isn't necessarily something you even need to know about in your own data. If you have the right instructions for humans to distinguish types of collars, and the machine learning algorithms to build off the top of that, whether it's to do the exact matching between terms like shawls and the images, or to optimize the search engine, itself a form of machine intelligence, then you're able to start making these kind of fine-grained systems work really accurately at scale. And just in case anyone was wondering, a shawl collar is a collar which is uninterrupted. So as you can see, that folded over collar there is one continuous curve. There are no lapels, there are no notches in that collar at all, or peaks. And so that's what makes it a shawl collar. I bet no one joined this meeting today expecting to understand fine-grained distinctions in lapels. But certainly this is one of the fun things that we see regularly, is that the way that companies might divide up the world into all kinds of taxonomies that we wouldn't think about ourselves is something that we can put human-in-the-loop processing on. So moving away from e-commerce, the next example is in enterprise software. And so in this case, the business wants to improve the customer experience by process automation. So this is with Workday, perhaps a software that many of you are using for things like submitting receipts. So in this case, again, starting with the business use case and thinking about how we can solve part of the business problems with machine learning, they want to improve the customer experience on Workday. In this case, they want to improve expense submission process. I love this use case because I'm sure most people listening have to submit expenses, and no one likes this. It's never a fun task. And so they want to reduce the manual time to enter a receipt. And so to do this, they want to automate recognition of things like the price, the date, the merchant, and address. So there's probably a large number of different expense software which are used by people among the listeners today, and we're happy to help with a lot of them. And we do this by improving text recognition, by improving bounding box localization. So this is an interesting use case where it effectively combines image recognition, so identifying, as you can see, those red bounding boxes, things like the date and the merchant, with natural language processing, with optimal character recognition to extract the particular dates. So this is something that, again, can combine human and machine processing. So a machine can take the first pass. If it's confident, then lucky you, your receipt has been expensed automatically and you can get about more productive things in your day. If it's not confident, then that might go to a human for review. And this might be implemented in different ways. In some cases, it might be humans behind the scenes who are doing this optimal character recognition. In other cases, unfortunately, it might go to you, the end user, who then has to manually type in the details of your receipt. So final use case today, and I think another really interesting one for computer vision, is robotics and the Internet of Things. And this process is business process automation. And so working with a company called Boston Nova, we're helping them determine stock levels on shelves. So as you can see here in this picture, that's a robot walking down the aisles, and it is trying to determine whether a stock is low or completely out on a given shelf there, so that those stores can make sure that they're always stocked up. So again, starting with the business problem, Boston Nova's customers want to improve the customer experience and get repeat customer business. And in order to do that, they need to improve the in-store experience of their customers. And one of the ways to improve the in-store experience is to make sure as many of the shelves are as fully stocked as possible. And in order to understand which shelves are fully stocked, they need to understand which products are understocked. And so then that brings us down to the machine learning problem. How can we determine what's a stock shelf and an empty shelf and identify products which are missing? And this is a great use case for human-in-the-loop processing, because identifying an empty shelf is actually not something that most, no pun intended, off-the-shelf computer vision algorithms are very good at. Almost all research into object identification in computer vision has gone into exactly that, identifying objects, not the absence of objects. And certainly this is a task that can be solved with computer vision, but it's just a little bit different. So the hard part here is identifying something which is out of stock, like you can see in the top left here. So there's a stock label, but nothing behind it, versus simply an empty shelf, something for which there is not meant to be stocked there at a given time. And so while this is something you can solve with computer vision, most of the off-the-shelf systems that you have for a task like this won't apply directly. They won't have an out-of-stock category. Even some of the more sophisticated techniques that people use in transfer learning are built on systems that we've shown don't really work for this use case. So this is a great way of making sure that when this robot sees something that's not certain about, at least this empty shelf on the bottom right, really empty or not, we can put this in front of a human for review, making sure that humans agree on this and there's quality control for the human entries, so that the robot can be then smarter about seeing similar shelves in the future. So here's another example here, and in this case, it'd also be the art of telling, okay, is this two labels for the same fruit, or is this really something that's missing right there? So this is the kind of human interface that you might have. So here, the task is broken down to say something like, all labels belong to visual product or product group. In this case, you could say that this does not. So that's it for the examples that we're going into. I'd love to turn it back over to Chris to lead the Q&A.
All right, thanks, Rob. Helps if I unmute my microphone before I start talking. So we got a couple questions here, and I believe this one was from the slide with the bird's eye view of the cars, and the question was, can this be deployed aerially via a drone in a live fashion? So I guess you would have not a stationary camera, but a moving camera as well as moving cars.
Yeah, absolutely. In fact, that particular shot, I believe, was taken from a drone. So whether it's a drone, a satellite, or a Cessna, these are things that could be taken with moving cameras as well as moving objects within the frame.
Okay, great. And now this question, I'm not certain if it was directed towards you or towards me, but I'll throw it out there for both of us to answer. Is to what degree do you leverage AWS Mechanical Turk?
Oh, we're big fans of Mechanical Turk at Figure Eight. So we have 100 different labor partners that we work with, and Mechanical Turk used to be one of those. It's actually not at the moment, but it's still certainly a company that, or an organization within AWS that we work closely with. So Figure Eight tends to work on large enterprise problems. And so often we'll find people who are building out a Mechanical Turk, and once they're looking for scalability and a broader workforce, they'll migrate to us. But certainly, they're friends of ours, and we send a lot of work each way.
All right, great, thanks. So just a couple more here. How do I know when I have a large enough set for training my data? So when is a data set large enough to begin training?
Yeah, that's a great question. It really depends on the use case, how much you want for a large data set, which I know is an answer that no one really likes to hear. So I like to say as a rule of thumb that for every category that you care about in your data, you'll start getting usable results after you have about 10,000 examples. So if you're caring about categories of clothing, then you'd want 10,000 examples for each of those categories. If you're doing something a little more complicated, like maybe pulling out keywords or entities from within text, then for each of those categories of keywords or entities, you'd want about 10,000. You will find that that'll vary a lot. So that 10,000 is can change by an order of magnitude. For easy tasks, it might be 1,000. For complicated ones, it might be 100. And so the best way to do this is to start collecting data, be smart about sampling, so you can use active learning to make the data count, and then measure the accuracy as you go. So always evaluate on a held out data set of randomly selected items to give you an accurate view of how your model really is performing. And then as you're adding new training items, you should be able to see that learning curve going up. And the steepness of that learning curve will tell you how much more you can gain from adding more training items. But yeah, if you just want that really simple answer, about 10,000 items per label is what you're looking for.
Great, thanks, Rob. And then when we say 10,000, let's say that we have a limited number of images per category. Can you, let's say, take an image and rotate it 90 degrees and create 4 images from that? What's been your experience about the benefits or lack of benefits of doing something like modifying an existing image?
It's pretty mixed. I've seen some great examples in doing exactly that. So especially if you know your images are fairly homogeneous. It's more common that rather than taking one image and then flipping or distorting or changing the resolution, that people will choose some combination of those methods per image. So it definitely increases the variety in your images, but not the overall volume. You do run the risk if you're doing any of those things, for example, and your image happens to be red, then all of a sudden you've got 10 red images. And that color could be de-weighted or incorrectly weighted rather in your model. And so it's always better to try and find additional data items to label. But certainly if that's not possible, then doing those kind of manipulations over the images can work. And not really yet making it into industry, but we're seeing a lot of really interesting work with generated and synthetic data. Just started to make it in the industry, especially in self-driving car community. So you can imagine where you have a rare event like a baby carriage, which is out of control and rolling down the hill towards a road. That probably doesn't exist in the millions and millions of hours of self-driving car data anywhere. But nonetheless, it's an event that the self-driving car companies need to know about. And so you'll see people thinking about ways to make synthetic data because we as humans can envisage that situation and react appropriately. But for companies rely on machine learning, they might think about how to generate that data.
Yeah, exactly. I've seen our partner NVIDIA has done some great work with simulators. They actually create an entire virtual reality environment for the vehicle to be trained in. So switching gears a little bit, can either of the speakers address the HITL use cases for security? When we say security here, I'm going to go out on a limb and say maybe physical site security, individual security, like a security guard style role.
Okay, great. We see a lot of use cases with different aspects of security. So everything from kind of like network intrusion detection to fraud detection, and with your use case then for outside security guards. In all cases, you can think of it as a funnel. So you have sensors looking at all your networks, maybe all the documents in your company for fraud security violations, and maybe cameras around your installation. And so your computer algorithm might not be good enough to completely automate the process, but from the millions of potential data points or camera images, it's able to see when something looks anomalous, when something looks out of the ordinary, and then it's able to put just those important anomalous items in front of humans for review. And historically, it wasn't really human in the loop. It was just kind of a one-way system like that with some basic rule-based filtering. But we're starting to see a lot more sophistication now where, for example, if someone says, no, that's a pedestrian walking by, or yes, that's someone trying to break into the building, where that feedback can go back into a machine learning system so it can become better at identifying those events going forward.
All right, thanks again, Rob. I'll give you a quick breather because I think the next question might be for AWS here. Can you expand on the smartphone video slide where inference is used to identify the scene as a party? And so what I'll recap that scene. That was a video feed sent into Rekognition Video, and you have the same options with a video feed as you do as an individual still. When you send an individual still to Rekognition, you have 5 or 6 different APIs that you can call, anywhere from celebrity recognition, essentially, are there any celebrities in this picture? That's a technology that's used with an Amazon Fire TV. If you're ever watching Fire TV and you pause the video and you see at the bottom of the screen some actors and actresses pop up, that's using that technology. Some people don't know that Amazon purchased the IMDb database some time ago. I thought it was a brilliant move because it was a delicious data set to do fun stuff like that, like celebrity recognition. Now, along those same lines, you can do facial recognition. Essentially, is there a face in this video or image? Then you can link that to what we call a face collection. Essentially, you can have a collection of 100,000 faces that are recognized. You can link that to like a DynamoDB database with a name, and the inference is going to come back. Yes, this face with this hash code is stored in your collection. Now, let me add this caveat. When I talk about a face collection, only the image vector is stored, and that vector cannot be deserialized or reversed in the event that somebody gets a hold of your credentials and accesses that face collection. So the image that's sent to Rekognition, that image is vectorized, and that vector is compared to the vector stored in the face collection. So what that video did was, once it saw that there was a gift, it saw balloons, it saw children with presents, it had enough information to infer that this is a party. Now, this is some proprietary technology that Amazon has put together. If we send simply a still of a living room, it would recognize a couch, an end table, a lamp. It would realize that it's indoors, so it might add that indoor label, and then also might add the exact room that it's in. It might say this is a living room or a family room. And when you send your image or video to the service, you're going to get a JSON response back, and it's going to attach not only the labels that it thinks it sees, but a confidence score. And that confidence score is going to range anywhere from 99%, even 100%. I've seen 100% with some Bruce Lee pictures, all the way down to whatever you feel comfortable is safe for you to use in production. If you want to say, I'm going to believe the machine up until 75%, and then I'm going to have to put a human in the loop, then that's your threshold for that. So, aws.amazon.com/Rekognition is going to have much more eloquent verbiage on that than myself. So if you want to check that out, lots more information for you there. Okay, so we got time for a couple more questions here. Can you give an example of image and video recognition currently in use in the medical field? I'll give one real quick, Rob. Then if you want to chime in, feel free. We have a partner working with radiologists to identify essentially tumors. This is a very, very high profile project where we're hoping for the best. It's got some great results thus far. Some of the challenges with radiology images is it's a 3D image. When we saw the example of the party, is simply a 2D image. When you have a scan, a CT scan or MRI scan, that's essential slices layered on top of each other. So it's very complicated to understand not only where you're at on the X and Y axis, but now we've added a Z axis. So some great work going on in that field. I don't have any examples I could talk about off the top of my head with video, but Rob, I don't know if you have any examples you want to talk about in the medical field.
Yeah, absolutely. And in fact, we treat 3D scans like videos to do the same kind of scrubbing. So yeah, I love this use case. Part of my PhD was focused on artificial intelligence for health. And then our head of computer vision here at Figure 8, when he was previously a postdoc at Harvard Medical School, he wrote the first paper showing that crowdsourced workers could be as accurate as trained physicians in labeling medical images, and more recently showed that deep learning could be as accurate as humans for some of these tasks. In both cases, cancer prediction from cells. So this is an area that we're still actively working in, and it sounds actually similar, Chris, to yours. So with one company we're working with, 3Scan, they're doing a lot of really exciting work where they're gradually taking very thin slices of tissues and building up very large 3D models. They're doing this on AWS, as a matter of fact. And they want to label each of these 3D objects as belonging to a particular organ or being a particular kind of cell, or in the case of a lung, maybe an air sac, so not part of the organ itself. And treating each slice as a frame, we can actually implement this as if it was an object tracking task in videos, so we can track that same object through 3 dimensions.
All right, great. Thank you very much, Rob. And that's going to bring us to time. So I want to thank everybody for attending today. I hope you found the session informative. There's some websites here, some URLs on the link. Linked here on the slide if you have any further questions. And also, I'll throw my personal email out here. It's Burnska, Burns, at Amazon.com. So if you have any questions, and I did not get to you here in the Q&A session, I do apologize. Feel free to reach out to me directly. And then I wanted to, recognize Rob Monroe one last time, CTO of Figure 8, fantastic partner. I love looking forward to the projects that they bring to the table and the good work they're doing. So thank you again, everyone, and hope you have a great day.
Thank you, Chris. Thank you all.